Yeah, good morning. Today's first talk is by Suresh Govindarajan. He is a faculty at IIT Madras, and his research interests are string theory and mathematical physics. Today he'll talk to us about partitions, a topic to which Ramanujan had a lot of contribution. And he'll talk about, he'll introduce us to this very interesting combinatorial problem and tell us about his recent research in the end too.
Good morning, everybody. First, I would like to thank the organizers, in particular Raghavan, who thought that I could talk about some mathematical topics. I am a professor of physics, but only a student of mathematics. And so I will try to do my best. And I would have liked to use the board, but I don't know. If I sit in the last row, I cannot read the board anymore. So I assume there might be people like me. And so I've used transparencies. If it was a classroom, I would have used a board. So I'm sorry to all the mathematical audience who will really like to go slow. But there is a way of making me go slow. Ask questions. Okay. So there's one more. This problem, I got into this problem because it's a problem which is very easy to state. High school kids can understand it. But there are a lot of questions you can ask, but the answers are not so easy. So it's very accessible to undergraduate students, and I have the privilege of teaching at IIT Madras, where we have lots of very smart undergraduate students. And so the idea was this was supposed to be a carrot to get them interested, and not too many people eat carrots apparently at IIT. So this is the outline of my talk, and so there will be a brief introduction, and then I will discuss what these objects, higher dimensional partitions are, and then I will introduce the idea of generating functions. This is a beautiful method where you can solve a large number of counting problems, and so I will give you examples, and then I will go to a slightly more technical part of the story, which is Hardy-Ramanujan-Rademacher formula. I will briefly sketch. Most of the things I will not give proofs, but I'll give you references, and finally I will, time permitting, I will discuss organizing partitions by symmetry and how some nice results come from this. But while this is my current agenda, I don't mind stopping at 0, 1, 2, 3 anywhere. So let's begin with a definition. And so a partition of any integer n greater than 0, you can put equal to 0 as a definition, is to express it as a sum of positive integers. So let's say, look at 2 plus 1 plus 1. See, that's an example of a partition of 4. But of course, there's an issue. I can write it as 1 plus 2 plus 1 and 2 plus 1 plus 1. And we do not want to differentiate these two guys. So to write a unique representative, you write it as a weakly decreasing sequence. So you write it as 2, 1, 1. By weakly decreasing, I mean the next guy in the entry is less than or equal to the previous entry. So this 2, 1, 1, sometimes I will not even put commas. I'll just say is a partition of 4. So one of the questions you would like to ask is how many, if you're given a number, integer, positive integer, how many partitions does it have? And we'll use the symbol P of n to denote that. So here I've written out all the partitions of 4. There are 5 of them. 4 itself is a partition into one part, and then this has 2 parts. It's 3, 1. This has also 2 parts, but it's 2, 2. This has 3 parts, and this is 4 parts. And a little bit of thought will tell you that P of 4, there are no more. And P of n is called the partition function. Now the first question which we can ask is, what is P of 200? Okay, question is, should we go around doing this kind of thing to get to the count? And the answer is yes, we can do it this way. These days we can write programs, and it can enumerate all those things, but you will get a screen full of gumph which you can read or sort it. Okay, but so you can do more refinements of the problem. You can, so I'm saying Pn, so this represents partitions of n which has r parts. Okay, so let's just go back. And so as I explained, this is just the number of terms. So this is a partition with 2 parts. Okay. In principle, I should be able to use this. Yeah. Similarly, so we can also define a partition of n whose largest part, L stands for largest, and this is supposed to be L. In the serif font, it looks like something else. So sans serif font rather. LP equal to R denote the number of partitions of n with largest part R. Okay, so if you take 2, 1, 1, it's a partition of 4 with 3 parts and largest part 2. Okay, so we can just go ahead, and it's a simple exercise to create this table where you just write a partition and ask how many parts it has and ask what is the largest part. So, but you can observe something. This observation goes back to Euler, which says that partitions, or here we can see that partitions of 4 with R parts is equal to partitions of 4 with whose largest part is R. It's true for all the values of R, 1, 2, 3, 4 which occur. Okay, so the claim is that this is true for all n, and in the later part of the talk we will see that we can prove this statement in a very, very elementary fashion. Okay, so before that we'll play a game, because these days most people love to play games. My son is a great one. Given a chance, he'll be playing some video games. So in my time the games were more elementary, but so we'll play a game. So the game is the following, where I have a square piece and I have gravity. So I'm a physicist, so I throw things down, so gravity will come there and settle down here. So after this I take a second piece, I drop it. It can fall here, it can fall here. It can fall like this, but if you jiggle it a bit, it will go to one of those things. So I will not allow unstable configurations. I am interested in stable configurations. Okay, so let's so the question, so here is a stable configuration of 4. Okay, so now the story of the game is you fix the number of pieces and you want to ask how many stable configurations exist. Okay, and as you will see, I can only count up to 4 more or less, and every time I will use an example which involves 4. So we'll fix that number to 4, and lo and behold, we see there are 5 possibilities. Okay, no more. Okay, and if you played a lot of a game called Tetris, have you heard of that? Okay, so you see that this doesn't have all the pieces. There are 2 other pieces which is not allowed because of the stability condition. Okay, but you can ask, can I allow those things? And that is also another counting problem, and that is homework for you. With 5 pieces, how many can I do that way? Okay, and so, but here the interesting thing here is when I took 4 pieces, I got exactly 5, and if you remember, partitions of 4 was also 5. Okay, so, but of course, depending on your area of specialization, there are people who, real mathematicians unlike me, who will recognize Young diagrams here, which is drawn Russian style. Okay, apparently Russians draw it this way, and Rajesh will recognize directed compact lattices, or in Ising model thing, these would be some kind of clusters. And of course, if you like me, who played a lot of Tetris blocks. Okay, so how do we, so the claim is that those pictures which I drew have a 1-to-1 correspondence with partitions, and you can, so now you can start drawing pictures, and these pictures have a name. It's named after a guy named Young. It's called Young diagrams. So now I will give you the construction. Given a partition, so what was the partition? It was some weakly decreasing sequence with entries A1, A2, A3. That means A2 is less than or equal to A3, such that the sum adds up to whatever is the integer n. You draw a Young diagram with AK boxes in the kth row. So if you take 3, 1, this is a partition of 4, my favorite number, and so you draw 3 boxes this way, 3 boxes this way, and if you rotate it, I think 135 degrees or something, right? So 135 degrees, it will go to one of those pieces, and 2, 2 goes to this guy. So it's clear that this map is a bijection, so this arrow goes 2 ways. If you look at this fellow, I can just quickly look at it. Okay, first row contains 3, second row contains 1, so it is 3, 1 over. So this is the way, this is proving, if you want to show that 2 sets are the same, the best way to do it is to construct a map which takes, given one element of set 1, you get an element of unique element of set 2 and do it in the reverse order also. That's a bijection. Okay? But one benefit from this story is that once you draw these pictures, there is some property which is not visible in an obvious fashion out here, and it is the following. So you think of x direction in this and y axis in this direction, and you carry out a flip, xy flip. Then you see that what it does is it takes one Young diagram to another Young diagram. But now what is this Young diagram? It is 2, 1, 1 from the rule we just worked out. So what we get is that this is an involution. If it acts twice, if you do it, it comes back to itself. So what it does, so this operation is called conjugation. So but now if you ask what does it do to partitions, you look at this guy, this we see that it maps a partition with R parts, okay. So this guy is a partition whose largest part is 3, while this has 3 parts. So what it does is it maps the partition with R parts to one with largest part. So this picture, it says that this is a bijection. So it's a map from a set to itself, but it gives you, sometimes it gives the same element, then you call it a self-conjugate partition. But it now gives you a very simple way of showing that the partitions of n with R parts must equal partitions of n whose largest part is R. It's extremely, it's reduced to looking at pictures operations, and if you take any book, lots of proofs of partitions can be reduced to playing tricks with diagrams. You take this diagram, you move this, you do this, it's really like child's play. But when you can show that it's a bijection, it shows that object on one side has one description, the object on the other side has another description, and they are equal. That's truly amazing. Okay, so but my talk is going to be on higher dimensional partitions, and so I need to define them. So we look at plane partitions, which are the next generalization, and after that we can just go to arbitrary dimensions. So this important figure in this was Percy McMahon, who was major in the British Army, and his first posting was in Madras. Okay, but apparently at some point he decided that he will do mathematics, and he turned out to be a great mathematician in the area of combinatorics. In fact, he's one of the fathers, I guess. Okay, so he proposed the following generalization of partitions. So you consider a two-dimensional or a plane partition. You start with an array now of integers a, I, j. So that means there are two directions, one along the I direction and one along the j direction, with the following property that it is weakly decreasing in each direction, such that the sum of all elements in the matrix or whatever is n. Okay, and now we can just put a subscript 2 to indicate the 2 dimensions. P2 of n denotes the number of plane partitions of n. Okay, so let's pick. So here, if you look here, you see guys which I can write in black, which are in one row. We have already seen these guys. So these are the partitions of 4, ordinary partitions. And then there are guys which are the same actually, but they are just a rotation. You just take 3, 1, and these 3, 1 is, they are related by just flipping. So those I think I've indicated in blue, have I? Or I missed something? 2, 1, 1, no, that is here. So are there 5 blues? Oh, 4 is the same, thank you. Okay, thanks. So yeah, so I haven't missed any. So you see that, so really the ones in red are the guys which really are not, are truly two-dimensional, if you wish. And this looks like a very elementary statement, but towards the end of the talk, time permitting, we will see that this has important implications. And now you can see that P2 of 4 is 13, and from this you can always see the easy point that all partitions of n are, two-dimensional partitions of n are greater than or equal to Okay, equal to is in some low numbers.
This second,
The-
first letter, the second row.
Yeah.
Why is it only two-dimensional?
It's got entries running this way, but there is a sense in which I will say that it's also I mean, you're right, I mean, but I don't want to I will just discuss that in a moment. Yeah. Okay.
Only two-dimensional.
Yeah, so Rajesh's point is, which we will see in a moment, that actually there is only one true two-dimensional partition, and that is this guy, and pictures are useful, so that's my next part of the story. And but I mean, for simplicity, I even included these guys, but I can convert these also into okay. So again, now we can draw Young diagrams, but now we have to go to one higher dimensions. Remember that when we started out with one-dimensional or ordinary partitions, we put squares. So we want to go to 3 dimensions. This analog of a square in 3D is called a cube. Okay, so the idea here is to construct to see the other extra dimension, and so here there is not so. Yeah. So this is I have put one cube. So you can think of this as the projection. So I can't draw 3 dimensions. So what I have done is to project along the 1, 1, 1 plane. I start looking. So this can be thought of as x, y, and z directions. So I put one guy, and so this is just 1. Next I can put here. I could put here, and next I put 2, 1, 1. And so just to point out what Rajesh was saying. So I wrote 1, 1, 1 as and said that I claimed that this is a 2-dimensional partition, and he was objecting to it. The reason is the following, is that if I lift this up and then if I project down, it will become 2, 1. Okay, so let me go back a little bit. And so once you write it as I'm going the wrong direction. So coming back to this, really what the point here is that for instance, this is when you look at this, the analog of conjugation which involves a 3rd dimension, I can make this into this, and so on and so forth. Okay, so for instance, this can become 2, 2. So these 3 will become. Okay, so we'll see this in a moment. So but here I want you to appreciate what we are doing, and so you see that you get Young diagrams again. So now this tells you that we can generalize Young diagrams to higher dimensions, of course replacing cubes with hypercubes in 4D and so on and so forth. Okay, but except now you can see that it gets much harder and harder to visualize. If you have a 4D cube, you may want, I mean, I can only, this plane is 2-dimensional, so I can do some projections, and I will show you some pictures, but after a while it's not worth thinking that way, and so one replaces these Young diagrams with Ferrers diagrams, and the idea is very simple. You just replace every square, cube, or whatever with a point. Okay, just think of shrinking every guy to a point, and so we'll give a second definition which you can go back and check. An unrestricted D-dimensional partition of n is a collection of n points which I'll call nodes in the positive orthent in D plus 1 dimensional space. So what is orthent? It is like the generalization of you say quadrant, octant. After some dimension, what do you say? So that's the orthent is the word. I had to look up the dictionary many years ago, so I learned one new word. Okay, in the positive orthent, satisfying the following property: if the collection contains a node with coordinates a1, so in D plus 1, so a1, a2 to ad plus 1 is the coordinate of this node, then all nodes which are in some sense with this property that they lie less than that, this is the stability condition, okay, also belong to it. That is the only condition. Okay, and then it's fun exercise to prove that this definition, at least for the case of plane and ordinary partitions, is the same. So let's look at this 1-dimensional partition of 4. So it's got 0, 0, first guy you have to place, 1, 0, 0, 1, and 0, 2. So let's look at this condition 0, 2. So there's nothing, we are not allowed negative numbers, so nothing less than 0, but 2 implies there should be 1 and 0 below that. So it contains that. So 0 is 2 is there, 0 1 and 0 0 is also there. So this is a valid partition. And again, drawing all these things, it's a pain. So I just usually just to write in compressed form, if you want to write, you can just write it like this. So remember that the columns give you the number of nodes. Every column is the coordinates of the node. Okay. Or equivalently, we could just write points here. You draw some axis. Now I'm not going to use x and y. I'll call it x1 and x2 because I can go to arbitrary dimensions. And here is the same partition. Or equivalently, this is the Young diagram. So you can see what is happening. You take the square, you squash it into a point. Look at this. Okay. So question is, where do these higher dimensional partitions appear? And they seem to disappear very fast. So I'm just giving a few examples. It's the infinite state Potts model in d+1 dimensions. If you have to do a little bit of tweaks in the higher temperature limit, you can show that there is a counting problem there, which is the same. And there is something called directed compact lattice animals. If you look at the definition, you'll realize it's the same. But more unusual is, for instance, where I came across the counting of something called BPS states in string theory and supersymmetric field theories. So, and quite often, sometimes you look at bounded plane partitions. They can appear as domino or tilings of a hexagon. So here are some pictures. So here is an example of so here we have a hexagon. So you can think of this as taking a plane partition which is lying inside a box whose boundary is given by this hexagon, and so you can see, if you look carefully, you see a 3D projection of cubes, and okay, so this is in fact the Young diagram of this. So once you go to higher dimensions, you have to do projections, and so here you notice that there are all tilings are done by rhombi or lozenges, as they are called, depending on which country you are from. And so there are, if you wish, there are 3 kinds of rhombi, this with different orientation, one rhombus with 3 orientation. But once you go to higher dimensions and you're projecting down to 2, you start getting complicated tilings with different kinds of tiles, and these appeared in physics in quasi-crystals, where you allow different kinds of tilings and things like that. Okay. So now I'll move on to the next part of my talk, which is how do we use generating functions to solve these problems. And so the idea is the following. So you just define P of 0 to be 1, just definition if you wish, and define the generating function of partitions P of Q as this form. So P of Q is nothing but, if you expand it as a power series about 0, the coefficient of Q power n gives you partitions of n, number of partitions of n. This is the definition. It looks very simple, there's nothing, okay. But why am I using the variable q, why not x? It's just some convention. So there is it's called q series sometimes. They have other meanings, okay. And sometimes it's related to some modular parameter. So Euler wrote this beautiful formula. So now here is the thing. This we didn't, so let's go back a bit. So let's look at this formula. It's an infinite product formula, okay. But if, so what you can do is, if you take this formula, suppose you are interested in some, say, the problem I gave, 200, right? What is P of 200? What you can do is take this formula and find the coefficient, do a power series, and get the coefficient of Q power 200. Today, in some standard program like Sage, Maxim, or Mathematica, or Maple, it's like this, okay? But you can do it in a second. Okay, so question is, how do we understand this formula? And I'm going to illustrate this for how you extract P of 4. Okay, so I just use simple what do you call, the Taylor expansion of 1 by 1 minus x, which is 1 plus x squared, so on and so forth. So I just look at this product and I expand, it goes from m equal to 1 to infinity, so the first term is 1 minus q. So you expand that 1 upon 1 minus q, so I just expand that. I get that as 1 plus q, and instead of writing q square, since I don't know 1 plus 1 is 2 yet, I write it as 1 plus 1. No, that's not the reason. The reason is that to remind you where it came from, that it came from the expansion of q power 1. So on and so forth. And since I'm not interested in terms beyond 4, I just truncate it. It's an infinite series, so I use order q power 5. So these are the 4 terms it will contribute. I go back, take the next term, 1 minus q square. 1 plus q square plus q power 2 plus 2, but the next term is q power 6, so it's larger than 4. So on and so forth. So, and I go up to 4, q power 4, the next term is q power 8, and the rest of whole rest of the infinite series will start with 5, so it will be at least order q power 5, so I'm not interested. Okay, so now all I have to do is to ask what are the terms which will contribute to q power 4 in here. So what I'm going to do here is mark in red the term I'm going to pick, and of course I have to show that q power 4 is one such term times 1 1 1. I'm not indicating the ones, I will only indicate the non-ones which I'm picking. So here I get q power 4. We can identify this with the partition of 4, which is 4. So we should see 5 terms. So here is 3 1, here is 2 plus 2, here is 2 1 1, and there should be one more, that is this. So we have recovered we have recovered all the 5 partitions of 4. So now you can see that this argument which I have used for 4 can be trivially extended for any n. Okay, and that's a fun exercise, and I strongly recommend that you. But what we see here is that this is a beautiful way of quite often it's the goal is not to just enumerate some bunch of partitions, but to look for what is the partition function, what is the generating function, and then you can do much more, okay, as you will see in this talk. Okay, so a few more examples. So the fact that you start thinking in terms of generating functions gives you nice things. So the generating function of partitions whose parts are less than or equal to m. Okay, we already saw that I truncated it. Let's say I was interested in looking at parts which are less than or equal to 4. Then whatever I did last time was enough if I kept going to extraordinary more terms. So you just restrict the terms in the product by m. And then you will see that that's the thing. In fact, you can do slightly better. Suppose you are interested in the generating function of partitions of n whose parts arise from some set S. So then you just restrict your product to m in those sets, and a little bit of thought will show you this. Okay, but you can do even more. You can refine your counting. Okay, so here I'm going to count partitions of n with r parts. Okay, and because I have 2 numbers here, I have to put 2 auxiliary variables. I call the second variable t. So I have a function of 2 variables q and t. If I Taylor expand it and look at the coefficient of q power n r, that will give me the answer. And this is a fun thing. You can see that this guy produces all parts which start with q power m. So you put a t out here, you will see that it counts the number of the power of t given by this q power m. When you expand it out, will tell you how many times, how many parts this term is contributing. So again, is this? Yeah, that is, yes. There is no t here. Thank you. I must be, thank you, cut and paste error. Okay, so you can refine things, you can do many more variable generalizations, but this is my idea here is to show you how people go around doing these things. And okay, so now I'm going to, if you want to evaluate partition of 200 and you are told that you do not have access to a computer other than the only computer you are allowed is in your top story, okay, and which was the case 100 years ago. And so the question is, how would such a person compute? Okay, so that's what I call a practical formula for P of n. So now we'll refine things. Let P of n with distinct parts, okay, denote the number of partitions of n with distinct parts. Okay, so key point here is that means if you looked at if you're picking a value of m as a part, it can only appear once. So I can no longer work with 1 upon 1 minus q power n, because if I Taylor expand that guy, it will give too many terms. So solution is very simple. Replace that guy by 1 plus qm. That will giving you exactly. Okay? So that guy has a very simple term. That's all it is. It's m equal to 1 to infinity into 1 minus q power n. Okay? Now I want to refine it a little bit more. What I want to do is, I want to distinguish between guys which have even number of distinct parts or odd number. Okay? So basically I want to put a minus sign in this thing, and now I'll leave it as an exercise to think that think about the fact that if I replace this plus with a minus 1, I get this required minus sign. Okay? One easy way is to ask the same question. If you want to have, you can write a 2 variable generalization, put a t out here, and then you can show that t equal to minus 1 gives that. Okay, that's one way. But what I like about, what is interesting about this guy is that this is exactly the inverse of the generating function of partitions. Okay? So we are going to use the fact that the product of this with the generating function is 1. Okay, very, very simple. Okay, but here I need a theorem which says that p of n with even distinct parts minus p of n with odd distinct parts, call it E of n. Then what Euler showed is that E of n is generically 0 except for some few numbers, and these are numbers of this kind, and if j is just positive, these were called pentagonal numbers, and you can look it up. Wikipedia has nice pictures. I didn't have time to draw the pictures, so but you need to include the plus sign, which you can do by letting j run over z, the full integers. Okay, so these are called generalized pentagonal numbers, and so only for these numbers these two are not equal. So you now this is where you can give a pictorial proof. So how would you give a proof of this? So you would take the Young diagram for, say, this is something which has even number of distinct parts, and then do some operations on it and make it into something which has odd parts, and then it will fail to be a bijection only sometimes, and E of n, if you wish, is the failure in some sense of it to be a bijection. Okay, so now so this E of so what we know now, this is just definition of this. So but from the previous page we know that the generating function of this is the inverse of the partition function. So I'm just writing this formula now. Okay, so I am using something from before, that pi this is equal to 1 plus E of n q power n. Okay, and then you just multiply these things, and then what you do is to look for the coefficient of some power of q, and then you will get this nice identity. Okay, what is beautiful about this is E of m only clicks when you hit a generalized pentagonal number. So this is an efficient algorithm to compute p of n recursively. Okay, so here are the first few generalized pentagonal numbers. So this is 1, which is j equal to 0. I think this is plus minus 1, they go in pairs. Okay, so now for instance, so we can there is this beautiful resource called Online Encyclopedia of Integer Sequences. Suppose you have this problem, you get a bunch of numbers, and you don't know what it is, what problem it counts. So what you do is the following: you go to this online page, and let's say by some brute force you know the first 5 numbers in there. You go there, you type the first 5 numbers. It's oeis.org. You type those 5 numbers, and it will show you a bunch of sequences which contain these. And then if you look below, if you are lucky, you will find that that there are many different problems which give these numbers, and quite often what it does, it gives you a handle on proving your thing. So you want to know the next guy in the sequence, and it looks impossible from your viewpoint. So what you do is to construct a bijection from your set to that one of those problems. Sometimes you get lucky. In one particular case, I found like some 25 entries, and I had to scratch my head and figure out which one was relevant for me. And then it turned out I got something, but there was a further refinement. So it taught me how to refine my counting. So I could do even better than this thing. So this is a modern tool where you can use this, but here, so if you want, so here you can see that P, so this just tells you P of n equal to P of n minus 1 plus P of n minus 2 minus so on and so forth. It's this thing. And with the rule that if once the argument becomes negative, you define them to be 0, so that it terminates. Okay? So Major Percy McMahon, he actually computed the first 200 numbers. So, and he found that P of 200 was this large number, and so you can see something 4 times 10 power 12. So obviously you are not going to sit there and count them by enumerating them. That's not the way to go. Okay, and this is also from an algorithmic viewpoint. People who do theoretical computer science want to know what is the computational complexity of their things. For this particular thing, P of n can be computed in n power 3 power half. Okay, but I am greedy guy. I want to know what is P of 10 power 20. Okay, there's a reason I'm picking this number. I know the answer. Okay, so that's a beautiful book. George Andrews has 2 books on partitions, but this is at a lower level. It's with Erickson. It's a beautiful book with lots of examples, and it's very elementary and wonderful book. And I strongly recommend people who are interested in this to look at this thing. Okay.
Are these faster than the analytic formula?
No, no way. You can't compute so that's the whole thing. So I will discuss later how you do that computation. Yeah. So similarly, you can go ahead and define the generating function for for all d-dimensional partitions in the same fashion. So I wrote here in a different fashion. I didn't define. You always define PD of 0 to be 1, so that you can then make this sum go from n equal to 0 to infinity. Okay. McMahon conjectured, and eventually he proved that the generating function looked very similar to that of the normal partitions, except there was a tweak. There was some m out here. If you would minus 1, we get the other one. So this is the only change. Okay, and eventually is by the way 20 years later. And don't expect me to give you a proof, elementary proof. In fact, I cannot, I mean, if you push me at a corner, I will prove it, but it will take some time. Okay. So, but you can use this formula to write a recursion of this kind. It's a little bit of work, but this formula implies this. Okay. But there is no analog of the pentagonal recursive formula, because remember, it was sparse. It had only fewer terms, so this is not that efficient. By the way, for partitions, ordinary partitions also we could write, except that I think this will become sigma 1. Okay, so so it's a divisor sum. So it's a sum of sigma 2 of k is the summation d divides k d square. It's a divisor sum. Okay. That's correct, right? So it's some standard number theoretic thing, and so these are very easy to compute numbers. So this is not okay. So what I want you to see here is not complicated things. Now that we are very comfortable with generating functions, so there is some black hole counting problem which I was involved with, and what you observe here is that you get product of this thing 24 powers of the generating function of partitions. Okay, and it comes with a factor of q, and for number theorists they will realize that this is a very important function. Okay, and and this is also a modular form, etc. of inverse of a modular form of weight 12 of the full modular group. Okay. But here is something which many people may not know. There is something called the Gopakumar-Vafa, or sometimes in this context the Donaldson-Thomas invariance on some manifold called the conifold. You look at this thing, there are several nice features of this formula, and which I observed long ago, and I was very interested in understanding this. And if you look at this formula, if I remove this if I put instead of minus, if I replace these with the so first thing you see is that this is exactly the McMahon generating function for plane partitions, but this is like some refinement. Okay, so you get a triple product. If instead of minus ends here it was 1, this almost becomes the Jacobi theta function. Okay, so but this so here we see Euler in this thing. So so it turns out that these counting problems are related in this case to colored plane partitions, and so there are people who have worked on this, and so plane partitions do have some meaning in some 2 physical applications. This is more sort of mathematical, but mathematical physics. Okay. Question is, what do we know about generating functions for d greater than 2? Okay. So McMahon was a very busy man. He did lots and lots of computations, examples, invented stuff. I mean, and so he had a conjecture. So he just noticed, oh, first one was 1, second one was n. Maybe the next one is he played around and tweaked it, and next one should be n plus 1 C2. He wrote, put some, you play with it. Some trivial exercise will show you that this works well. Okay, so obviously this works for d equal to 1 and 2, and he conjectured that it holds, but it was shown in 67 by Atkin et al. That it fails. Okay, so and as of today we do not know a generating function for, we do not have a simple formula, and I think Rajesh will agree with me, we don't believe that there exists, because if there was one, we would have found it. No, actually there are many other reasons. Okay, so I just want to also discuss why lots of people ask, why is it we have never heard of these guys? By the way, d equal to 3 you call it solid partitions, for instance. Okay, why people have not looked at these things? Okay, so the point is, you could say it is uninteresting, but if you look at the name of the mathematicians who have worked on these things, they are all big names. McDonald's worked on symmetric polynomials, among many other things, and the McDonald identities in Lie algebras, affine Lie algebras. Okay, so this paper of Atkin et al. Involves 4 people. Atkin was a number theorist. Bradley, who is actually a very interesting guy, is a computer science guy. And but he worked a lot with these people, MacDonald and Mackay. Mackay is famous for his moonshine and also working with the classification of finite simple groups. For instance, he was very actively involved. He told me that his greatest thing was to write the character table for the monster. So they wrote programs and this stuff. So this is, in the 60s they had to go punch cards, take it somewhere, and these people were like, they were in their mid-20s, of course. Today they are in their 70s. So they did all sorts of things, all sorts of computations, and this was one of them. But so Birch wrote a. So they see, it's like a bunch. Characters have to satisfy a bunch of constraints. So bits and pieces of entries. So I don't know, chicken and egg. I think the proof of monster, I don't know the details. Actually, I should know, but I don't know. So okay. So I'll just read what they have said. So this is Birch mentioning the reaction to this paper, or 1967 paper, where they showed that the conjecture of McDonald was wrong, but McMahon was wrong. But we also believe that McMahon himself may have known it, but he never wrote it anywhere. So I cannot resist to mention 1967D, which is this paper on m-dimensional partitions. At that time, the authors complained that no one seemed to know anything about them, except in the first 2 cases. Ordinary partitions correspond to m equal to 2 in their notation, and the case m equal to 3 more often known as plane partitions. And very little seems to have happened to be discovered since. There is a note on this subject in 1971. In the words of the third author, that is MacDonald, the paper landed like a lead balloon, but they look genuinely interesting. I mean, I know that every time I write a paper, it lands like a lead balloon because nobody reads it. So, except for some 3 guys in the world somewhere. Okay. So, but Stanley also is another important person in combinatorics. He's written this beautiful 2-volume series of books called the title is Enumerative Combinatorics. And I think you should read, I think, the Introduction to Enumerative Combinatorics Volume 2. That is something which will take you only 1 hour, but you should read. Okay? And Stanley also writes this, the case R equal to 2 as well-developed theory. Here, two-dimensional partitions are known as plane partitions. See 21 in the blah, blah, blah. For R greater than, what I want you to tell you, for R greater than 3, nothing, almost nothing is known, and some proposition casts only a faint glimmer of light on the vast darkness. That's what he called it. Okay? So obviously, generating function is not the way to go. So brute force is the way to go. And so two algorithms, one which was used in the Atkin et al. Paper is due to Bratley and Mackay. It's in 1967, and another one due to Knuth. Knuth's algorithm enumerates something else. So computer science people look at something called topological sequences in a partially ordered set. Okay, doesn't matter what that means, but if you choose that set to be ND, then you can show that you'll get a bunch of numbers of topological sequences that if you convolve it with the generating function, convolve it with the normal ordinary partitions, you get the partitions of D. There's some theorem of his. So what he did was to write a program, and you're doing this, and he actually wrote the first 28 numbers. And then this was extended by Rajesh and his collaborator Mustonen to 50 in 2002. And and in 2010 I posed this problem: what is P3 of 100 to a bunch of students? And Srivatsan, who is sitting there in the audience, actually went and he liked this paper, and immediately he wrote a program, and he said, "Sir, it works very well." I said, "Yeah, what is this thing? It works fast, sir. What is solid partition of 20? He said, "Oh, it gives it like this." 25, it was not working. I said, "This is not good enough. You have to do something. Rajesh and co have done 50. We at least have to do one number, 51." Okay, and so probably in his 10th attempt, he came up with an amazing, what I think is a non-trivial extension of Knuth's algorithm. And there is beautiful mathematics underlying this, which we discovered later. And we were able to extend this we added 22 numbers. Not a lot, I know, yeah, but 72 took only 500,000 CPU hours. Without Srivatsan's algorithm, I don't think so. I think it would have stayed at 52 or 53. Okay, so adding more numbers is not easy, but I mean, there is a project which I run. It's available. You type the partitions project or whatever. That's probably the first page on Google. Okay, so you can see that this number is a number of order 10 power 18. We have exactly enumerated it. This is what we get. Okay, so generating functions are not on brute enumeration. So another thing it's like when you're sinking, you're looking for a clutch. I mean, you're looking for something. Some straw is good enough. So one of the things, people, the directed compact lattice animals community, they showed something very nice. So Bhatia et al. So they showed that asymptotically, that means if you take some power, log of this thing, it goes to a constant. Okay, and because you know the generating function, you can evaluate C1, C2. Zeta of 2 is some pi square upon 6, but I just want to show some uniformity. So you get C1 and C2, but what about C3? So Mustonen and Rajesh didn't just enumerate 50 things. They did something very nice. They used a Monte Carlo simulation and estimated C3, and they got this. And the most interesting observation, at least to me, was that if you took the wrong generating function, so M3 here represents to, you take the wrong generating function of McMahon and just look at the coefficient. And so because you know the generating function, you can estimate this, and you get some formula. You can see, in fact, it is a simple exercise to write what that, and that should be 1.7898, and you see it's pretty good. And so they had a conjecture which said that actually C3, even though this formula for M3n is, the generating function is wrong, it captures the asymptotics correctly. But life is very cruel, at least I think. So Nicola de Stanville got in. I never met this guy. I mean, I met him eventually, but he was looking at another situation, and so where they found discrepancy from a similar McMahon type formula, and he said, why is it it seems to work in this case, but not in my example. I said, no, we don't know that. We only know this much. We need to check more. So then we both embarked on asking, how can we really check this thing? And this was fairly long because we wanted to be sure. And so we found that C3 is actually 1.822 plus or minus 0.001, which for me, very disappointingly, it disproves the conjecture.
So that one is not a proved result, it's an estimate.
This one?
Rajesh.
No, these we cannot, these are only estimates.
This is also an estimate.
Yeah, this is also similar. It's a different Monte Carlo program, but it is a similar estimate. Just okay. So, but so these come with error bars. So. No, that's because you're looking within 1 sigma. You're looking 1 sigma. These, so you have to look at higher. Like you be like a particle physicist, say that at least 5 sigma or something. Yeah. Huh? Yeah.
No, you wrote P there on the left hand side.
P3. This is for 3. Yeah, thanks. So no, this was for 3. The proposal was that this is the answer.
Second sigma is very small.
So, yeah.
Huh?
The second sigma is really small.
Yes.
Sigma is like
Yeah, it depends. The typical Monte Carlo run of mine was like about 1.5 months, and many runs. Because we really wanted to be sure, and so. But we saw there are some beautiful patterns, results, oscillations that we observed in this because we had to create nice data, and we hope so that will shed some glimmer of light. It's not all negative, but okay. So how much time do I have? 20 minutes. Good enough. Okay, so this part of my talk is going to be slightly non-elementary, will require higher level mathematics, in the sense, higher by that I mean you need to know Cauchy residue theorem, some little bit of complex analysis. Okay, so this is a formula due to Hardy-Ramanujan and Rademacher, which enables one to actually compute P of 10 power 20 today. Okay, we do not use the pentagonal formula, you will run out of memory. And so how does it work? So this is just standard thing. You know the generating function. You know the generating function, and you just take a contour, circling the which is, I'm just choosing it to be a circle, but any contour which lies within a disk of radius 1, and the contour should go around the origin in counterclockwise fashion, and then you get a simple application of Cauchy residue formula will tell you that this will give you P of n. But let's look at this function P of q. It's a product of it's the inverse of the product of 1 minus q power m. Okay, so when does it blow up? It has poles. It has poles of different on the unit circle. That means when q. So q is nice inside the disk, but if you try to enlarge the thing, every time you pick a rational point, that is a point which is, I forgot an I out here, q equal to e power 2 pi I h upon k. So k can take any value, but h, so that you get a primitive root of unity, h should lie between 1 to k minus 1, with h k being coprime. Okay. So the strength of the pole decreases with increasing k. So you have to so the idea here is to actually do these calculations in the neighborhood of these singularities, because the bulk of the contribution will come from there. Okay, but this idea of strength, you can make it more precise, but what do I mean? Let's take k equal to 1, that is just q equal to 1, every term in the product blows up, right? But if you take k equal to 2, then it's h equal to 1, so that's q equal to minus 1. Then a term like 1 minus q cubed will not blow up at q equal to minus 1. So in some sense it's weaker, and crudely speaking, this is not precise, you can make it very precise, but So what it says is that you can organize them in terms of increasing value of k, and the dominant contribution will appear for k equal to 1. Next subdominant would be k equal to 2, k equal to 3. There is a nice this thing, you can organize things, and you have to do some contour stuff which I am skipping. There is nice connection with something called Ferrers sequences, again I am skipping that. So you can estimate these things, and you can estimate the contribution by using something called the method of steepest descent. And so for instance, if you take k equal to 1, you get a nice formula. And if you remember, I wrote log of Pn with some prefactor was some constant, and if you that constant should be C1 in that notation, and that is pi root 2 by 3, which can be written again in terms as I think some 2 square root of zeta of 2. Okay. So you can just ask how good is this formula. So I just did nothing, I just plugged n equal to 200 and it gave this number, not so bad. If you remember, the exact number was some 3.98 into 10 power 12. Okay. So this was 1917, Hardy and Ramanujan, they computed all the contribution, they didn't just do it, and Hardy comments that he's surprised that nobody did it before them, because it was, I mean, you did asymptotics for so many things, but nobody did it for this. And Ramanujan apparently felt that there was an exact formula, he kept insisting that, and so they both worked on this thing, and but they obtained an asymptotic formula. So asymptotic formula, I'll give you a crude definition of it. It's suppose you are adding a bunch of terms, the error in that thing will first go down, and after some point it will start increasing, and an estimate for the error is given by the magnitude of the last term which you add. Okay, so that's the rough thing. So they got some series, and so they have to sum. So this summation here should be summation k equal to 1 to infinity and sum over all h's which are co-prime. So this is the sum over all roots of unity, and then this is the estimate. Okay, and their formula did not involve, I mean, it's not usually written in terms of Bessel function, but it is a simple Bessel function which can be written in terms of the hyperbolic functions. Okay, for half integer values the Bessel function is simple. So you get so this is the sum over all the contributions. And what happened is Rademacher was going to teach, it was like now summer break, and next semester he had to teach a course where he was planning to do the Hardy-Ramanujan formula, and he was preparing for the lectures, and he noticed that they had not done some errors, they hadn't done some things properly, and he tweaked it. Okay, and the tweak turned out to be a very interesting one, and it led this formula which was asymptotic to a convergent series. So if it's a convergent series, it's very nice. I can truncate it wherever I want, and I know what the, I mean, if the error in the terms which I have thrown out is less than 1, because I know p of n is an integer. If the error is 0.01, I don't care. Okay, so they introduced a tweak, and the tweak was the following, that you truncate this sum, but you truncate it in a manner which depends on n. This looks very simple, but this is a big deal. This was the first time somebody really did this, and so you have n of n, and then it says that n of n you could choose some constant here, but should go as n power half. And so the structure is the following. There is always this e power minus 2 pi I n h by k, that is just that term which was there actually already there, and this is a nice sum which is called a Dedekind sum. This is just what you call this function, what is this function called? Ramp function, or a sawtooth function, okay, or a Bernoulli polynomial. And dk is this thing, and the thing here is, you could say, if you're interested in large n, this minus 1 by 24 doesn't mean anything, but actually this in fact it's interesting. I think Hardy and Ramanujan kept the minus 1 by 24 because it came in their computation. And so if you do these things, and it looks like a nice formula. And remember in 1917 when they didn't know about this convergent part. So here's what Hardy has to say. At this point we may have stopped had it not been for Major McMahon's love of computation. McMahon was a practiced and enthusiastic computer, something got eaten up, computer who created a table of p of n up to n equal to 200. Okay. So what do? Now you have a formula, and somebody has taken the trouble to compute 200. So you want the largest value, so they took n equal to 200. Of course, we naturally took this value as a test for our asymptotic formula. We expected a good result with an error of perhaps 1 or 2 figures, and we had never dared to hope for such a result as we found. Okay? So they added 8 terms in the series, but if you look at the n power half, actually it's enough to stop at 5, I think, but you go a little bit more to be sure. And when they added the numbers, they found that the error was just this. Okay? So the formula, as they put it, was asymptotic and exact. It's very unusual. Asymptotic series usually they are bad, you know, after some point the error is this thing, but here you're guaranteed that the error is, you can always choose enough terms and the errors were less than 1. Okay? So this table was taken from the other book of Andrews, which I mentioned. Okay. So coming now, the key point here is the problem with the pentagonal formula is that you need, if you want to compute p 10 power 20, you have to compute a whole bunch of stuff which is below, and also the complexity was n power 3 by 2. Okay? So Friedrich Johansen showed that the HRR formula is almost optimal. The reason, his definition of optimal is the following: if a number has n a certain number of bits, if you have to do that many computations to do the thing. So the number of bits in the partitions of n goes as n power half. So it's truly, if you find anything which goes like n power half, it's optimal. So he, up to this log n's, it's actually optimal, almost optimal. So he was able to compute p of 10 power 20 using the HRR formula, and there's a nice, so this was only fairly recently on March 2nd, 2014. But he also has invented a lot. I mean, you have to remember, you have to do arbitrary precision mathematics. You need to be sure about how you will handle errors, etc. He created something called ball something, where your estimates lie within a ball, and it's done computationally. Okay, it took, I mean, it took about 4.5 days on a computer, but he's got this result. Okay. So I asked myself if there was a formula, similar formula for plane partitions, and for plane partitions you know that the generating function is similar. It also has poles, but there's a power of m, but who cares? We can still do that. And then there's a person, a number theorist named Almquist, who had done a lot of work on that thing, and with a student who was a student at IIT, now he's a graduate student at Stony Brook, we obtained an asymptotic formula for plane partitions. Okay? And it's not asymptotic like the Hardy-Ramanujan with our Rademacher thing, that cannot go away, this thing. And the formula looks similar. So again you see there's a HK sum which is truncated at n power n, and n power n goes as some constant power n power 1/3. Okay? And then there are more Dedekind sums, but the real tweak here is that there is a second summation, and it has, in some sense, is related to the fact that the generating function of plane partitions is not a modular object. Okay? Here we cannot use modular transforms, we have to use other methods. Okay? For those who are experts, this is the statement. So you end up with an infinite series which for every k is asymptotic. So you need to truncate that fellow. So you truncate it at an optimal point where the error is a minimum. You can do it when you do it on a computer, you do it numerically, but if you want to write a proof, you actually have estimates for it, and so we have estimates for that, and so n star goes like this. There's even better estimate, so it goes like n power 1/3 times k. So you get a extra summation which was not there in the Hardy-Ramanujan-Rademacher formula. You also get a new special function which we call the Almquist function, which is can be written in terms of some generalized hypergeometric 0f2. It's a solution to a third order differential equation, ordinary differential equation, and some nice beautiful Dedekind sums come in the process. And the last bit here is that this formula, we have an estimate for the error. Okay? And you look here that this, it's exponentially suppressed by, forget about k, put k equal to 1 for simplicity. It's suppressed by n power 1/3, but this term is growing. But you get one is getting lucky. Look at the coefficient in front of this, it's about 30. Okay. So then if you put this formula and ask when does it become bad, you will find that when does the error become order 1 for what value of n, you get something like 5500, but this is only an estimate. It turns out in practice that it's actually errors are in control up to 6400. So this formula with this truncation is exact up to 6400, and I believe I can make it exact up to about 50,000 by handling the errors even better. And so numerically I have checked for 10,000 for instance. Okay. So this is the statement, it's exact for n less than 6425, and here's an example. So I had 17 terms out here and there's some long. So it's P2 of 750, this is the exact answer below and the error is 0.167. Okay. But I'm a physicist and this shows, I mean I wanted to implement it on a computer where you can just plug it in at least up to these numbers. But then that recursive formula here was beating my formula very easily, and because by factors of some 30 or something. And so I thought it was, I was making fun of this formula, saying that it's a theoretical formula which has no practical use. But today I have a good implementation. I sat down and optimized it, and today it's faster than this formula. So probably the fastest way now to compute at least P2 of 6425. 10 seconds. No, it was, my first attempt was 25 minutes. 25 minutes versus 85 seconds, and now it is 75 versus 75 seconds. Okay, so I have 5 more minutes, so I will just briefly discuss something and stop. So this is to, I mean this is really banging your head against the wall, asking can I make progress with higher dimensional partitions? And the answer is yes, surprising yes. Okay, so first thing is to just ask what is the analog of conjugation in higher dimensional partitions. So there it was XY exchange. You should think in terms of Young diagrams or Ferrers diagrams. So what would you do? You have many more axes, you can permute all of them. So the generalization of conjugation is the permutation group, and it just permutes. So you can organize all the Ferrers diagrams or Young diagrams by the action of this thing. So I did that for the case of plane partitions where it becomes S3. Okay, there are 3 axes. And now again Rajesh's earlier remark, remember these are all, so they get related. So these are, so you only see one guy which is very, very special. This guy is invariant under S3 action. It goes to itself. So we call such partitions totally symmetric plane partitions. Okay, and this is something which will, that's all I need. Okay, so this once you put them in a box, there's an extra symmetry called complementarity. So his talk can be thought of as a talk on totally symmetric self-complementary plane partitions, right? Okay. Also known as alternating sign matrices. That's a bijection. Okay. So more generally, what you will do is to look for, you know, H is some invariance group of your I mean H is a subgroup of S3 which leaves your partitions invariant, and then you will find that, you know, these numbers of these guys is related to dimensions of cosets. Okay. So but when you take 4, what you will find is that you will miss one group, it's called C3, and if you can ask when you can find something which is invariant under C3 but not S3, you will find it first at n equal to 13. And homework, construct that plane partition. It's not hard. Okay. So in my last 2-3 minutes, I'll tell you simplifications happen if you treat partitions in all dimensions on the same footing. Don't differentiate between them. We already saw this, right? I mean here we saw that really these guys, they are not really 2-dimensional. Okay. So good question. So you have to. So the answer to that is what you do is you take the nodes. I don't know the answer, but for I know for S3 and S4, yes, the answer is true. But in general, I don't know. For instance, I mean I wanted to ask. So let's take, you know, 12 S12, M12 is a subgroup. I've been playing with Mathieu groups recently, so you know, are there. So the answer to that is very simple. You just take the action on pick a node and act on it and see if its orbits lie. If you cannot find nodes which are in the orbit of the correct size, then that cannot happen. So all may not happen in general. There's no guarantee. So you have to, that's the thing. So you asked, so I went the other way here, I asked yes, and the answer is yes. Okay. Did I? So the idea here is to consider a partition of 2 in 1, 2, 3 n dimensions. So you see here the 0, 1, you add, this is a normal partition. I can convert it into a 2-dimensional partition by adding zeros. This is boring, you're not doing anything, you're only just adding zeros. So what is happening in this thing is that all these nodes actually lie in a 1-dimensional hyperplane. So clearly you can define something, so you ask if all the nodes lie in some r-dimensional hyperplane, you call that as a partition, partition with intrinsic dimension r. This is the true dimensionality of that thing. It's not the d which we are associating. And then, so you can see things like all partitions of 2 have intrinsic dimension r. So if you give me a d-dimensional partition with intrinsic dimension r, then it will be trivially invariant under SD plus 1 minus r, because it will act on the 0 space. So in this example it is S3. Permuting these, it does nothing. There are just zeros. Okay, and doesn't act on the minimal hyperplane. So what it does here is that I will skip a bit more. Yeah, so what you can do is to define a strict FD of dimension d as so I want to pick, so I say a Ferrers diagram is strict if its intrinsic dimension is equal to d plus 1. Okay, so in other words, that is the smallest dimension into which it can fit. Okay, so then you can define A and R to be the number of strict Ferrers diagrams with ID equal to R and n nodes. This is a nice combinatoric problem, and you can count it actually. Okay, and you can ask what is the relation. This is just some symmetric, this is just some binomial thing which you can just argue based on symmetry grounds, and you get this transform. So A and R is related to this, and so I am showing some computations here, that's not important. And so if you see here, this matrix is only triangular, and the key is if you pick a particular int n, you will see that the number of 0 entries here are n minus, non-zero entries are n minus 1. Okay, so that tells you if you want to compute partition of 10, you need 9 numbers. What? No, they are not all. No, they are not Stirling numbers. No, some might be. Maybe this one? No, it's not. It's not. Okay, so this will be my last transparency. After that, so key is that there is another transform to A. It leads you to a F matrix. So this is the A matrix, and then you get something which has far fewer terms, and this has n minus 1 upon 2 the integer part of that number of entries. So with this, I've been able to compute partitions of up to 26 in any dimension. Okay, so thank you.
Any questions?
So does this McMahon's formula for solid partitions underestimate the actual number, or
there's a so this is one question. So for low values, whenever we all suspected that the McMahon M3 of n will be greater than P3 of n, but our numerical simulations have shown that around n equal to 1400 and around 1400 actually they overtake. It has to happen because the asymptotic value is 1.822, which is larger than 1.7898. So it has to overtake it, but luckily the overtaking point could have happened very, very far away. It happened around in thousands, where the data is very good. So yeah, we could answer that question. In fact, it was posed by Atkin et al. Is this always true? And the answer is no. For larger than that, We expect this the number of solid partitions. In fact, my hope originally was that you try to ask for a bijection between these two things and understand how it fails. Okay, and but that I haven't made progress. Some esoteric things, yes. So there is something when you look at the Hilbert scheme of points on CD. If you compute Euler characteristic, not the there is one Euler characteristic which gives the McMahon numbers and another thing which will give P3.
Any more? If not, let's thank Suresh for a very nice talk. So now there's tea, and then 11:30 is the next talk.